Hello, mm, good morning everyone. So today is the second session of additive manufacturing and its application in mechanical engineering. So as per the previous session, you know what are the types of additive manufacturing. If you want, I can give you a small recap right now. So there were four important types of additive manufacturing. First was FDM, fused deposition modeling. As we know, it was low cost, but it has low variance, means do many of the things you cannot do many of the things with the help of fused deposition modeling, since it was very limited to the usage. Second of all, it was stereolithography. It has high resolution, means the quality of the parts which will be printed will be very smooth surface finished. Now it's about digital light processing. It's not very used right now in India, of course, but it is very uh, what can we say, efficient, because it is very fast compared to the traditional stereolithography. Now let's start about the design for additive manufacturing. As per the title, you can know what it really means. It is additive manufacturing in the designing perspective. Design. What is, first of all, let us know what is design in additive manufacturing. Design is not something like the poster or anything you have in the colleges poster, anything. Design is like a particular solid part must be simulated in a virtual environment before, so as to replicate it into 3D printing. Let me give you a quick example of what are the different softwares. First of all, there are SolidWorks. SolidWorks is a premium version, so you have to buy it from the store. But second, if you want to do it free designing, then it's Creo student version. You can do 3D designing from there. And there is also a software which is very basic and it's available online, Tinkercad. I would not recommend you to do Tinkercad for high complex geometries, but yeah, it's very viable option for the new beginners. Now let us learn about the importance of designing specifically for 3D printing. As per the presentation of slide, there are 5 points and there are 8 points in total. Exploiting complex geometries. Complex geometries is like something that has a large application in day-to-day world. Means even if you see a normal door, there are a lot of different type of extruded cuts on it. That is not possible with the help of simple manufacturing capacity right now, or humanly possible. It is first designed in the 3D environment, or say virtual environment. Then it is then printed on the um, 3D printers. Now second, optimizing for additive processes. I guess you have learned it in the previous session, so I don't need to go through all of it. Reducing material usage through lattice structures. Material usage. For example, material usage is something like if you have to make a hole in the normal cuboid, you say. mm, If we do not do design before extruding it, you have to make the whole cuboid and cutting it through manufacturing capacity. But that is such a time wastage or material wastage. So we usually avoid it with the help of designing. Fourth, tailoring for layer orientation. Orientation, I know you know the gist of it. Orientation means the view, you can say view. Fifth is minimizing support structures. Support structures is for the 3D printed geometry. There are various support structures given to it so as to the printed model is means क्या बोलते usable. Sixth, topological optimization for performance. It enhances performance in summarize if you have to summarize this point. Customization and rapid prototyping. Rapid prototyping is like mass production and aligning with future trends, of course, the necessary one. Now let us go through these one by one. What is exploiting complex geometries? Importance. 3D printing allows for the creation of intricate and complex geometries that are challenging or impossible with traditional manufacturing. Designing for 3D printing enables the exploration and utilization of complex shapes and internal structure, emphasizing the principles of DFAM. DFAM is designing for additive manufacturing. So from these 2 points, what we can interface. 3D printing allows for the creation of intricate and complex geometries. Complex geometries, it helps in the build, building complex geometries in the virtual environment, as per my previous. Importance of optimizing for additive processes. Importance. Traditional manufacturing methods may not fully leverage the advantages of additive manufacturing. DFM guides designer to optimize structures for additive processes, ensuring that benefits of layer by layer constructions are maximized. Pretty clear. Reducing material usage through lattice structures. Importance. Additive manufacturing allows for the creation of lightweight yet strong lattice structure. Lightweight yet strong means I can say anything which is hollow but too strong. Means the density is low, but the material is strong. Now DFM encourages the use of lattice structures to reduce material usage while maintaining structural integrity, aligning with the principles of lightweighting. The principle of lightweighting is pretty complex at the BTech level, so I would like to avoid this topic, but I can give you the simple example of what is lightweighting. For example, have you seen a rubber ball and a jumping ball? Both are actually of same weight, but why is the rubber ball just rubber ball coefficient of restitution is basically 1, means whatever impact it gets on the ground, it converts it into velocity and jumps upwards. It's the difference in the lattice structure as well as the material that is being used. Now let us go in tailoring for layer orientation. Importance. The orientation of layers during 3D printing affects mechanical properties. Mechanical properties, you know, this all the types of mechanical properties. Designing specifically for 3D printing involves optimizing layers orientation to enhance strength, reduce anisotropy, and achieve desired performance. Anisotropy means that there must be different types of properties in different direction of the material. So we have to reduce it and go to the isotropic side of the material point of view. That basically enhances the performance. Now fifth, minimizing support structures. Important. Support structures can be necessary for overhanging features during 3D printing, but add complexity and post-processing efforts. DFA means designing for additive manufacturing guides designers to minimize the need for support structures, reducing material waste and simplifying post-processing. Post-processing means, actually it has been covered in the last session that post-processing is all the things after the 3D printing, means you have to remove the material and everything, and also the support structures. These comes in the part of post-processing. Now let us go to topological optimization for performance. Importance. Topological optimization, a key DFA, key designing principle, is best utilized in the context of additive manufacturing. Topological optimization. Designing for 3D printing involves applying topological optimization to create structures that are both lightweight and performance driven. So basically making a material or making a structure which is just lightweight doesn't fulfill the criteria about how that part should be used in the modern day-to-day world. It should also be performance driven, means it should be efficient as well. Now customization and rapid prototyping. Importance. 3D printing allows for the efficient production of customized and prototype parts. DFAM emphasizes the rapid prototyping capabilities of 3D printing, enabling iterative design. Iterative means repetitive design processes and quick product development. So rapid prototyping, as it seems from the word, that we have to mass produce in a quickest way if you want to decipher the value from it. Now aligning with future trends. Importance. As 3D technology advances, designing specifically for this manufacturing method ensures alignment with future trends. Keeping an eye on emerging materials, processes and technologies, DFAM encourages design that can capitalize on future developments in additive manufacturing. So additive manufacturing is a recent topic and as well as a hot topic. So aligning it with future trends means whatever new discoveries as per se in the whole world in the respective of additive manufacturing comes, we have to change the trend of our whole additive manufacturing concept right now. be it taught in India or anywhere else in the world. Now there are certain design guidelines. One second. There are certain design guidelines, or should we say best practices, we should do while designing a particular model in for additive manufacturing. First of all, watertight geometry. Watertight geometry means intricate geometry. We should not let even a 0.01 millimeter difference while making a simulative model in a virtual environment. Second, wall thickness. Wall thickness means whatever 2D sketch you make, you have to give it a certain thickness. So it should have a certain amount of wall thickness which may help the model to sustain in 3D printing. Third of all, overhangs and support structures. As discussed earlier, support structures are something that helps in the viable, viable processing of the 3D parts. Fourth, avoid fine details. Fine details as per se, because there are something called as tolerance. Tolerance means compensation geometry. Compensation geometry can be said that we have to give a certain amount of 0.4 to 5 error, so that if it is built in the real world, we can avoid the error of the if, for example, if we have given certain geometry and as per say the printing process had some deformity and the part was not printed correctly, so we should give some tolerance level that even if the deformity happens, the part can sustain in the world, because a 3D printing process is very expensive. Fifth, orientation, exact file format. File format, as per se, we have discussed in the earlier session that STL, stereolithography. STL is a universal format. If you are designing in say Creo, SolidWorks, Tinkercad and any other CAD software, but you want it to be printed in a particular 3D printer, you have to convert it into a STL file, because it basically divides divides your whole model into small triangular shapes which help in the printing processes. Seventh, scale means 1 millimeter, 2 millimeter, whatever. And check for intersecting geometry. Intersecting geometry means, for example, you are making two different circles and you are giving in an extrude millimeter means 10 inches thickness, but due to some orientation gap or anything, the two circles, or now it has become cylinder due to the thickness, intersects a bit. While printing, that intersected part might collide and the whole structure may break down, so you have to check for the intersecting geometry. Now let's discuss about the best practices. Prototype and test. Print prototypes to test the feasibility of your design before committing to a final version. Means whatever prototype you have built, you have to print it to just to check that it can be used or viable in the current scenario. Second, material selection. Choose the appropriate material for your application. Different materials have varying print. Means even if your model is correct and everything, but we make any model with the assumption that it will be made from this material, because for example a rubber ball and a plastic ball has different elastic coefficients, and we have the same 3D model, so there must be some kind of judging criteria for the material selection. Now let's go for simplify complex geometry. Means, yeah, we should do complex geometry, that's what us mechanical engineer do for the 4 years, but we also have a job to explain our geometry to the people who are not yet experienced in the field. So what we must do, anything that complexized our whole geometry or our whole 3D model, we should simplify it on the basic of a 7-year-old toddler. So we have to simplify intricate design that may be difficult to print or require extensive supports. Now let's talk about print bed adhesion. Adhesion means anything which sticks, means Fevicol, anything. Ensure proper bed adhesion by using features like a brim or raft, especially for models with a small contact area. For example, there is a small contact area. Let us give an example that there is a ball and that's lying on a floor, and you just put a small Fevicol between the between the floor and the ball. But the next moment you see, when you try to topple the ball, the ball just rolls over, because there is very less, means a pinpoint contact area between the wall and the ball. So we have to give a proper bed adhesion, means we have to give a layer adhesion to the um, brim, means there are features like brim of raft, and we have to give it in a 3D geometry while designing, so that the small contact area doesn't disrupt while 3D printing. Now let's talk about post processing. Plan for post processing steps such as sanding or smoothing to enhance the final appearance. Sanding or smoothing. Smoothing means that any it actually explains the third part of our simplify complex geometry, that anything which is not even or which is not level to a surface, we try to level it, not we do not try to level it on such a scale that the whole geometry breaks down, but yeah, we try to do it on a certain level that our whole uh, means our whole idea to how the 3D print model should look must be achieved. Now let us talk about documentation. Provide clear documentation including assembly instruction if applicable to guide users in post processing and assembling printed parts. Let me give you an example that while coding, if you are somehow familiar with coding, there is certain feature called as comments. So what is comments actually? It actually helps someone who has not written that code specifically to understand what particular the part code says and what the particular part code achieves while executing the command. Same goes for designing perspective. We try to give a smaller clear documentation such that whenever who will be assembling our part design must know where the meeting function or where we have to assemble the parts without actually have to ask to the particular designer of that part design. Means it eases the pose whole idea. Now let us talk about some of the designing part for 3D printing software tools. So I have given you a gist of idea that there were a few SolidWorks and all, but let me give you some more example for computer aided designs. CAD, Fusion 360, a powerful cloud-based CAD tool suitable for both beginners and Tinkercad, an easy to use web-based CAD tool suitable for beginners. Let me give you a simulation that it is Tinkercad interface. Now let us give you, you choose a keyword, you can change the shape, you can actually give 45, the unit is up to you, 100. Now change this one 45, this one 45, and now you can see one thing, that there are two keyboards right now. I was trying to explain you the intersecting geometry part, and this is what an intersecting geometry looks like. There are two different part design. When made on the same interface, it actually intersects. And now what will happen when we try to 3D print this part? Yes, you guessed it right, that it will break down. We have to avoid it by any cost, and what we can do is just drag it, as simple as that. This is Tinkercad, and I actually, for those who are hardcore mechanical engineers or who want to stay in the core side of the mechanical engineers, I would not recommend you, since it's not that usable for hardcore mechanical engineering. I would actually recommend SolidWorks, which looks like this. You have to buy this, it's a premium version, or you can just search Creo student version, it's actually free on the web. Now let's give you a simple example. This is a rectangle. Oh, sorry. Now we have to select a pane. It's a rectangle. Now we must give it some thickness. Extrude. Example 2 inches. Now this looks like this. Pretty easy. Now what I wanted you to learn, means what I wanted you to mean from the complex geometry part. For example, I have to do more sketching on this particular surface. I make another rectangle on this surface. I extrude it, means not extrude actually, sorry, extrude, cut it. what, for example, 5 inches. Now see what our design looks like this. Now more. One second. Now another one, another sketching done on this particular surface. For example, I'm making a simple face type structure on a, now another extrude cut part. See, this is just an example of how you can just complex any part, any simple keyboard. I will just give you one of my projects. It was these type of projects basically comprises of complex projects. It's just a part design. I will not give you the. It was a mechanical tail for a mechanical bird. Or I can give you another example which will make my point clear. See, this was the mechanical bird that I drew. Looks pretty awesome. Yeah, this is what we mechanical engineers do in the CAD software. So if you ever get a free time or if you ever get interested in what happens in this field, please try to download one of these few softwares. Now there is mesh repair tools. Apart from CAD designing, computer aided designing, we have another thing. We have mesh repair tools that if your design have some type of anomaly which cannot be detected in the CAD software itself, we have mesh repair tools. There are two things for this: Mesh Lab and NetFab. I have used Mesh Lab once and I'm not familiar with NetFab actually. But yeah, these two are one of the most used mesh repair tools right now on the web. Now, third is slicing software. Slicing software is actually very good. Means it basically eases your whole process of 3D CAD software. Means slicing a particular design comes under the part of 3D CAD designing. But actually we have made it another branch or another software tool just for the sake that the 3D CAD designing just can just be 3D CAD designing and there is no need to think means there is no need for a designer to think from the perspective of additive manufacturing. In slicing software we basically slice an STL model into the ways that we want. Means for example we have made that whole bird thing, we saved it in STL file. Now for example I just want the head of it or I would just want the tail of the whole part design. So what we used Cura or Prusa slicer. We just slice it according to our own need and just save it in a 3D printer. Now it's 3D printing community platforms Thingiverse, My Mini Factory. It will be discussed later. Now let us designing a small part for 3D printing. Step 1, create a Tinkercad account. If you want I can wait so that you can do step by step with us, or I should go with the session and you guys can watch it again for reference. Let us do the second part. It's just that I have made an account on Tinkercad, I just show. Then you have to start a new design, log into Tinkercad and click on new design. Now step 3, design the keychain. Actually import custom logo. Click on import and select the SVG file of your custom logo, adjust the size as needed, create keychain shape. Let me do it in SolidWorks, that would be more interesting. One second. For example, let's see how that's the problem with lot of apps open simultaneously. Okay, we select a plane. How does a keychain look actually? Let me see. Let's see a circle. Hmm, Now I should give a pretty. Okay. There is a trim function known as trim entities. Just we trim this part, and now. Mhm. And remember this as a tip that whenever you have to extrude or give a thickness to a surface, you always have to make a whole surface. Means you cannot just make a semicircle and extrude it. You have to give it a diameter or a particular line segment to make it a full 3D close sketch that can be extruded. Now we just extrude it. For example, what 1 inch, 2 inch. I'm not familiar with keychains, but if it looks like this, now we just make a hole there. Just select this plane, sketch. Mm, mm, then we extrude cut it. See how does it look? Now we just make a key and keyring all that. Basically, that gives you the idea how does a 3D CAD sketch works right now. You can I can read it one time for the sake of Tinkercad as well. Click on import and select the SVG file of your custom logo. Adjust the size as needed. Create keychain shape that I just made right now. Drag and drop a box from the geometric panel to the work plane. Resize and position it from the base of the chain. Combine shape. Use the group function to combine the logo and the keychain base. Select both elements and click group in the toolbar. So group function. There are different types of means for CATIA. CATIA it's assembly. For SolidWorks it's called mate function. For Tinkercad it's group function. There are different types of words that are used to describe the assembly function in different CAD softwares. But we do actually know what assembly means. And it totally means that we have to assemble all the part design that we have made separately into a single CAD model. Now let's add hole for the keyring that I just did. Drag and drop cylinder from the geometric panel, decide and position it and where you want the hole for the keyring. Now fifth, combine shapes. Use the group function to combine the keychain with the logo and the hole for the keyring. Text can be added easily. That is not something that you must be taught at this age. Now fourth, step 4, adjust and finalize. Adjust the size and position of the keychain to your liking. Add text which is optional. And third, group and export. And choose the STL file format. Uh, Let me give you how. Ah, the keychain is gone. Here it is. 5. Click save as. Now here it is written SolidWorks save as type. Now just change and here you will find an STL file. For example, I save it in 3D. Yes, I want to say. Mm, Here is a part 4, and we can actually view it in a 3D viewer, which is given in almost every laptop right now or PC. See how does it look? We can change the color, we can change the shades and all. This is what is the feature of STL5 stereolithography, and now we can just do insert it in the 3D printer and we can just print the part. That's what the beauty of STL files are. Now let us get back to the topic, additive manufacturing. Now fifth is download and print. Download the STL file to your computer. Use slicing software to prepare the model for 3D printing. We slice the software, adjust print setting, height, infill and support. Print the keychain and post processing, which is optional, which totally depends on you. That's it. That's it for the steps, I guess. Yeah. Now let me give you some of the examples of printer which is used right now in this world. Hmm. See, this is one of the most used 3D printers right now. Stratasys for F123. It is three varying degrees of performance capability. They bring fast professional grade 3D printing to the office environment, combining the plug and play ease of consumer product with the proven and tested result of the technology. The design reflects what the machine really is, a robotic tool. Hmm. That thing I read is of no use, sorry. So just from the image you can decipher what is going on. We just open the compartment where the 3D printing is happening. We just put whatever the 3D model is right now and we just give the material. We feed the material to the printer, and later on, after the whole completion of the process, the 3D printed part comes out just like this man is holding. This is what 3D printers do. Don't be misjudged from the fact that printing takes usually 10 to 15 minutes. It's usually more than that. For example, let me do check one thing. Give you an example. See, hmm, how much do you think this part generally took to build? See, how many parts are there? Surfaces from mesh, mesh, mesh. Everything is meshed right now. Do you know what meshing means? Meshing means to make a particular 3D object viable for 3D CAD modeling. We mesh model it. There is an option here called as mesh modeling. We can convert any body to this, just like, see, the inner riveted parts are being mesh modeled. You cannot reference both graphic geometry and standard geometry in this feature. Oh, actually this is the final product, so I cannot actually change it. But there is a file somewhere where this is all an STL file and I can show you all the triangular facets there are right now. So you can actually get the gist of it. Now let us get back to the topic, additive manufacturing. What happens? So in the previous session, we talked about what are the materials used in additive manufacturing. Let me get back to that topic and just recap it a bit. Additive manufacturing passes various materials across different technologies, each offering specific properties suitable for diverse applications. Here is an overview of materials commonly used in additive manufacturing and their properties. Polymers: acrylonitrile butadiene styrene (ABS). Its properties are tough, impact resistant, and versatile. Versatile means can be used in a lot of things. Polyacid, polylast, polylactic acid. I haven't heard about this term. This is new to me as well. I am also learning. Now, third point is polyamide nylon. Strong, flexible, and chemical resistance, suitable for selective laser sintering printers. Selective laser sintering printers. Let me just search. See, this was. We actually use, where, where is the picture? New powder. It's an infrared laser which helps in the hardening of the material or powder substances. Sintering means, hardened substance. And now new powder. This powder is deposited layer by layer, and the infrared laser, according to the 3D geometry, fade into the system, the STL file. We make the part. Now let us learn a bit about SLA and SLS technologies. Selective laser sintering, which is exactly what goes on the heart of this kind of 3D printers. The keyword here is sintering, which is the process of compacting and forming a solid mass of material by heat and or pressure without melting it to the point of liquefaction. See, anything which any material which is being hardened without making it liquid means not too much pressure or too much compact on that particular object, just to make a 3D model without making any of the part liquefied, is called selective laser, or we can say the principle of selective laser sintering. Inside this SLS 3D printers, a thin layer of material powder is applied on top of the building surfaces. All of this inside a hot chamber with the temperature just under the material sintering point. Immediately after that, a powerful laser beam draws a 2D section of the object on the surface, increasing the temperature above the sintering temperature on a tiny spot, and hence sintering the powdered particles is done. Let me open up something else. 1 minute, give me 1 minute. Mhm. Hmm. Traditional design for manufacturing. Rules for or guidelines deeply rooted in the designer's mind and severely restricted designers to further improve product functional performance by taking advantages of these unique capabilities brought by the AIM, the additive manufacturing process. Moreover, traditional feature-based CAD tools are also difficult to deal with the irregular geometry for the improvement of the functional performance. To solve these issues, design methods or tools are needed to help designer to take full advantage of design freedom provided by AM processes. These design methods or tools can be categorized as design for additive manufacturing. Design for additive manufacturing is the art, science and skill to design for manufacturability using 3D printers. Different from traditional manufacturing, this additive design process empowers engineers to create more intricate shapes and production parts while reducing weight and material consumption. It increases efficiency and design flexibility, and it reduces cost for businesses. So everything comes at last to the business perspective, and why not? That's what generally provides us the profit in the in this new world. So let us get back on the topic. Where was I? Hmm. Hmm. Polymers. Now let's talk about metals. Stainless steel properties: corrosion resistant, strong and durable, commonly used in direct metal laser sintering (DMLS) or selective laser smelting (SLM). Titanium alloy. Just I'm not telling you to remember everything by heart, because I don't want you to learn all the slides on the basis of face value. I want you to learn everything a bit by bit. So try to learn the properties first and try to relate the properties to the actual material. For example, corrosion resistant, strong and durable. Anything, if steel is corrosive, what we make it? Stainless steel. That's what happens. So just corrosion resistant, strong and durable stainless steel. It is used in DMLS, direct metal laser sintering, and selective laser melting. Titanium alloy properties: lightweight, high strength to weight ratio, and biocompatible. Widely used in aerospace and medical implants. Properties: lightweight aluminum alloy, lightweight, good strength to weight ratio, high strength to weight ratio for titanium alloy, and good strength to weight ratio for aluminum alloy, and corrosion resistant. Once again. Huh. Used in aerospace, automotive, and engineering application. Cobalt chrome alloy. So these are means it is actually covered in the last session. So I won't go in the depth of it. I just want you to at least remember some of the materials as to know, as to show that you have learned additive manufacturing. Hmm. Now, where was I? Design for additive manufacturing. Since Tinkercad has been mentioned in my slides, so I should go a little bit deep in Tinkercad, I guess. Mm, from where should I start so that you can get the gist of how a 3D model should work? This was the text bar which was discussed. You have to write anything. Hello. And there's a group function that helps you in the grouping of. And this is duplicate. Control plus D, just repeat everything. This is control plus C, copy, delete, undo. And this is store. That's not important part. This is cruise. This is import and export. You can export this in your file, and this is the STL file that I was talking about. You just repealing model, downloading model, and the model just get downloaded in the download bar. And when we try to open it, see how does it look. Hello. Because I have clicked the particular hello, then I have tried to export the model. Hence, the all the cuboids and all the stuffs which we drew earlier isn't in the final CAD model. We can light rotation, many things there. This for shadow thing, we can actually even change the saturation value. I don't recommend you to change it from 100, and it's the intensity. Means you can see the change if the stream is clear, and environment, everything. Means you will know what will happen in it, and it's a mixed reality option that I see. I can just change. This is hello, and this is me. I can just use my camera, and generally a 3D model is always transparent, so you can use it any of the mixed reality options. So this is all about Tinkercad. Import, export, send to means you can send it to any of your friend. Uh, so that's it for DFAM. I guess there is nothing more to learn in designing perspective for additive manufacturing, since additive manufacturing is a concept in itself. So I guess going in depth for designing is not suitable right now for this course curriculum. So thank you for attending my session, and please join us in the next session.